Have you ever really watched a machine at work? Not just the big parts, but the tiny pieces moving in sync. Think of a steam locomotive's wheels or a sewing machine's needle. Each part follows a precise, choreographed path. This isn't random. Every movement is engineered for a purpose. Machines create complex, invisible shapes as they work. Mechanical ballets happening all around us. Take windshield wipers. Their sweeping motion is the result of clever linkages beneath the surface. We rarely notice, but these motions are feats of creativity and problem-solving. The secret: turning simple rotation into useful, intricate motion. At the heart of this is the concept of coupler curves. Coupler curves are the hidden paths traced by points on a machine's moving parts. They're how machines translate basic motion into something extraordinary. Whether guiding a tool or mimicking a living creature, coupler curves make it possible. Understanding them is like getting a backstage pass to engineering's greatest show. So, let's pull back the curtain and explore what coupler curves are, how they're made, and why they matter. From the Industrial Revolution to tomorrow's robots, these curves are a cornerstone of innovation. Let's build our understanding from the ground up. To understand coupler curves, start with the four-bar linkage, the foundation of mechanism design. Picture four rigid bars connected by pivots, forming a loop. One bar is fixed, the others move. The input bar, or crank, is powered, like a bicycle pedal. The coupler link connects the crank to the output bar, called the rocker. As the crank turns, the coupler translates that motion, causing the rocker to swing. The coupler is where the magic happens. It both rotates and translates, creating complex motion. Imagine taping a tiny LED to the coupler. As the mechanism cycles, the LED traces a unique path in the air. That path is the coupler curve. Depending on where you place the LED, you get a different curve, near the crank, in the middle, or on an extension. This gives engineers a vast palette of possible motions from a simple mechanism. The coupler curve is the secret ingredient behind many machine motions. It's how we turn basic rotation into almost any path we need. 4 bars, endless possibilities. This is the starting point for understanding the art of motion design. Let's see how these curves are actually created. So, how do we generate a coupler curve? Traditionally, engineers drew the 4-bar linkage on paper, marked a point on the coupler, and rotated the crank in small steps. Each time, they'd plot the new position of the point, connecting the dots to reveal the curve. It was painstaking, but it brought the hidden path to life. Mathematically, it's about using vectors and trigonometry to calculate the position of the coupler point for each crank angle. With computers, this process is automated. Thousands of points can be calculated instantly, producing a smooth, precise curve. Modern software does what used to take hours in seconds. Whether by hand or by code, the principle is the same. Track a single point on a moving link as it follows a constrained path. This is the foundation of mechanism analysis and design. By understanding these curves, engineers can predict and control the motion of machines. It's the bridge between geometry and real-world movement. Every coupler curve starts with a simple idea: follow the path of a point as the linkage cycles. The result: a blueprint for motion. This process unlocks the creative potential of mechanical design. It's how we choreograph the dance of machines. Now, let's look at some famous curves and the problems they solved. Some coupler curves have changed history. James Watt's linkage, for example, was designed to guide steam engine pistons in a nearly straight line, revolutionizing efficiency. Watt's curve isn't perfectly straight, but it was good enough to power the Industrial Revolution. Later, the Peaucellier-Lipkin linkage achieved a mathematically perfect straight line using a more complex mechanism. These inventions show the power of clever geometry in solving real engineering challenges. Other famous linkages, like Chebyshev's and Hokin's, also create near straight lines with simpler designs. Each of these curves is a ready-made solution for specific motion problems. They're the greatest hits of mechanical engineering. Studying them reveals the ingenuity behind everyday machines. Coupler curves aren't just theory, they're everywhere. In engines, the connecting rod's motion is a classic coupler curve, crucial for smooth operation. Car suspensions use linkages to keep tires flat on the road, following carefully designed curves for safety and performance. Heavy machinery like loaders use linkages to keep buckets level as they lift, thanks to coupler curves. Even sewing machines rely on these curves to move needles and feed fabric precisely. Convertible car roofs fold away in a complex dance of linkages, all choreographed by coupler curves. These hidden paths solve real problems, making machines efficient and reliable. They're the silent workhorses of modern life. Every time you see a smooth, controlled motion, there's likely a coupler curve behind it. They turn simple parts into sophisticated solutions. That's the power of motion design. Designing with coupler curves used to be slow, manual work. Engineers relied on atlases of pre-plotted curves to find the right motion. Today, computers and CAD software have revolutionized the process. We can instantly model linkages, tweak dimensions, and see the resulting curve in real time. This rapid feedback makes design intuitive and efficient. Synthesis tools let us specify the motion we want, and the software finds a linkage to match. We can optimize for strength, speed, or efficiency, testing dozens of designs virtually. Digital prototyping saves time and money, turning linkage design into a precise science. The art of motion has become more powerful than ever. Modern tools unlock new possibilities for creative engineering. Coupler curves are more than textbook curiosities. They're the DNA of mechanical design. They show how simple geometry can solve complex problems elegantly. From steam engines to smartphones, these invisible paths shape our world. Even in the age of robotics and AI, simple linkages often outperform complex systems for many tasks. The genius of the coupler curve is its simplicity and reliability. Studying them teaches creative problem-solving and the art of motion. As technology advances, coupler curves will power everything from prosthetics to satellites. The dance of the coupler link is timeless. As long as we build machines, we'll choreograph their motion with these elegant curves. It's a beautiful, unending frontier for creators and engineers.